Welcome to the course Inorganic Made Easy. So as the name suggests, this is going to be a course which is going to be very helpful for all the students who fear inorganic chemistry. We are putting up lectures for you, which is going to make the study really easy for you. And also it is going to make the learning very scoring also for you, especially for the examinations, that is JEE Mains, Advanced and Neet. So what are we going to discuss today? Well, we are going to talk about the heating effects on oxides. If you look at the playlist in Organic Made Easy, you will be seeing many lectures on heating effects on metal carbonates, bicarbonates, hydroxides, metal sulfates, metal nitrates, and so on. So this is going to be a continuation or a part of that discussion where we are talking about the heating effects on various metal salts and acids. We have also created a separate playlist for all these lectures so that you can watch all of them. You do not miss a single one of them because this is going to be very, very important. Because here what we are discussing is from all the chapters of inorganic chemistry, be it hydrogen, be it S block elements, be it P block elements, T block elements. We are talking about everything in this discussion. This is going to be very, very helpful to you because you know at the end you have to learn everything and you are going to be tested on everything. So this will be one very important discussion for you people. Now, I am Dr. Ritu Johar from the channel H2O, the A to Z of chemistry, and I hope you're going to enjoy your learning with me. And trust me, this is going to be very important. Now, as we are going to discuss these heating effects, these are essentially thermal decomposition reactions. So before we begin with the discussion about the thermal decomposition of oxides, you should have a clear understanding what we mean by thermal decomposition. If you have watched my previous lectures on metal carbonates, bicarbonates, etc., there are about 4-5 lectures I have posted before the recording of this lecture. Well, this is going to be something common to all the lectures. If you have watched those previous lectures, you can just move forward this lecture by about 3-4 minutes. So otherwise you can revise it with me because this is going to make your concepts always stronger. So first of all, what do we mean by thermal decomposition? So thermal decomposition, essentially thermal means heat and decomposition means breakdown. So it is going to be breakdown of a compound when we are going to heat that compound, and that is going to result in the formation of two or more products from one reactant. For example, we have lithium nitrate. When we are going to heat it, it will be giving us lithium oxide, NO2 gas and oxygen. So how do we learn the metal nitrate heating effects is what I have already discussed. Similarly, metal carbonates, bicarbonates, hydroxides, sulfates, and then we have also discussed about the heating effects of the metal ammonium salts. Again, each and every lecture, please do watch it because we have put a lot of effort into it and this will be really very fruitful for you people. All right, now here very importantly for the thermal decomposition reactions, what you have to remember is that in all of these reactions there will be only one reactant. We will be heating that one compound and seeing what it is going to break down into. All right, and now in all these reactions, what you will be seeing is all of them, these are endothermic reactions. Endothermic reactions means that energy has to be supplied to the reaction, right? And why do we need to supply energy? Because we have to break these bonds present in between the atoms forming the compound. So that is why all the decomposition reactions, be it thermal, electrical, any type of decomposition reaction, these are always going to be endothermic reaction. Energy has to be supplied. And when we say thermal decomposition, so energy has to be supplied in the form of heat. Now, as we are going to learn the thermal decomposition of oxides, even the carbonates, the bicarbonates, the hydroxides, what we have been trying to do is to divide all the metals that we have into a few classes. And then we are going to break them into a few classes. What you will have to do is only learn about that one class or group of metals, how their metal salts will be behaving. And if any one of that metal from the particular class comes, you know what the product is going to be. So here we are going to classify the metals into three classes. Three classes: class 1, class 2, class 3. Class 1 metals are going to be all the group 1 elements, that is the alkali metals except lithium. All right. So when we will be learning about the oxides of the alkali metals, they are going to behave in a particular way. Then when we are going to talk about the class 2 metals, they are going to be all the rest of the metals. For example, we have lithium, which we did not include in class 1. All the group 2 elements like beryllium, magnesium, calcium, strontium, barium. Then we have zinc, copper. You can see these are the common metals that we have from the D block elements. Then lead, we have tin, which are from the P block elements, the lower down metals of the P block. So all you know that P block elements up the group, they are non-metals. As we go down the group, they are metallic in behavior, and their salts, which are all the metals which we have for class 2, they will be behaving in a particular fashion. And then we have the class 3 metals, which are going to be silver and mercury. So essentially what you have to learn is the class 1 metals, they are group 1 elements except lithium. Class 3 elements, they are silver and mercury. And do remember, just keep gold and platinum separately because they generally do not form any salts, being noble metals. All right. And rest all the metals which are not even in this list, you can put them safely into class 2. Okay, so this is the classification of the metals to learn about the thermal decomposition of their various salts, be it oxides, be it carbonates, be it hydroxides, be it nitrates, be it sulfates. Okay. Now, to make your work more simpler, I am going to even give you a trick to remember these three classes. And the trick is that you just have to memorize the activity series for the various metals that you learned in class 10th while you were studying about the metals and non-metals, right? And the activity series was going down the activity series from potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver. The reactivity of the metals decreases. That is what you have learned. Then you must have learned some mnemonic also to remember that activity series. I have also put one over here, but whatever mnemonic you have learned, I am perfectly fine with that. What I want is that you know this activity series. And if you know this activity series, on the top you can see sodium and potassium, right? So these are what metals? These are the alkali metals, that is the group 1 elements. And therefore what you have to remember is all the alkali metals except lithium, they will be forming the class 1 metals. So the top two and the rest of the alkali metals remaining, which will be cesium and rubidium, because you have to exclude lithium, and francium we do not put into the discussion, so we will not be having it over here. So all the alkali metals except lithium are going to be class 1. So the first two, and then you move on to the last two, that is mercury and silver. These will be the class 3 metals, and remaining all in between, they are going to be class 2 metals. So I think this will be easy. Now when we are talking about the oxides over here, one very important thing that you have to remember is that down the activity series, you know that the activity of the metals decreases. There is one more thing which is decreasing over here. As we are going to move down this activity series, the affinity of the metals for the oxygen is also going to decrease. So this is one thing that you remember. And if you remember this thing, well, you can learn the thermal decomposition of oxides very easily. And then if you watch my previous lectures on carbonates, the bicarbonates, the hydroxides, sulfates, the nitrates, again, if I'm going to give you the results of the thermal decomposition oxides of these three classes, you actually know the results earlier also. So let me make you understand how. So first of all, we have the class 1 metal oxides. That means the oxides of all the alkali metals except lithium. So they are going to be thermally stable to heat, which means that they will not be decomposing. As you're going to raise the temperature of the metal oxides, they are going to melt because they are solids. So they will be melting out, but they will not be decomposing and forming newer compounds. That is what do we mean by no decomposition. So for example, if we are going to heat sodium oxide, it is going to be melting down, but no decomposition. Similarly, potassium oxide, rubidium oxide, and cesium oxide, there is going to be no decomposition for them. So similar is going to be the case with the class 2 metal oxides. They will also be thermally stable to heat. that means that again, when we're going to heat them, there is going to be no decomposition product that will be formed. Only the compounds which are in the solid state, they will be melting down into the liquids. All right. And then we have magnesium oxide for an example, no decomposition taking place. Lithium oxide, no decomposition. Calcium oxide, lead oxide, zinc oxide, aluminium oxide, no decomposition taking place. So all the class 2 metals, only what you have to remember is what are the metals in that class. If you remember what are the metals in that class, you will be knowing that no new compound is going to be formed. We move on to the class 3 metal oxides. So these metal oxides, when they will be heated, well, they are going to decompose to form metal and oxygen gas. All right. So for example, the class 3 metal is going to be silver. So silver oxide, when we are going to heat it, it will be forming silver and oxygen. And then the next metal was mercury. So mercury oxide on heating, this will be giving us mercury and oxygen. Now, why did I tell you that if you watched my previous lectures on thermal decomposition of carbonates, the hydroxides, the sulfates, the nitrates, because this is what you could have realized even from those lectures. Let me show you how. Now let us take the example of metal sulfates. It is going to be similar for carbonates, the hydroxide, the nitrates also. Okay. So what we have for the class 1 metal sulfates was that when we heat them, they do not show any decomposition. Class 2 metal sulfates, when we heat them, they form metal oxide and sulfur trioxide. And class 3 metal sulfates, when we heat them, they form metal plus oxygen plus sulfur trioxide. So what this means is, here the class 1 metal sulfates, they are stable. All right. So they are not breaking down further. So there is no question of seeing a metal oxide over here. Even the sulfates, they were stable. Okay. But then there is going to be metal oxide also, that will be also stable to heat. Here what you can see is the class 2 metal sulfates, they are forming a metal oxide and sulfur trioxide. What we learned in that lecture was that even if you increase the temperature beyond 800 degrees Celsius, sulfur trioxide, this breaks into sulfur dioxide and oxygen, but the metal oxide remains stable. Right. So what do we deduce from here? That the metal oxides of class 2 metals, they are stable. They will not be decomposing. And that is what we have learned in this lecture. And then we have the class 3 metal sulfates. They break down into metal plus oxygen and sulfur trioxide. So what this means is that here, one decomposing, the metal oxide which was formed, that breaks further into metal and oxygen. And that is what we have learned in this lecture. Class 1 metal oxides, no decomposition. Class 2 metal oxides, no decomposition. And class 3 metal oxides, they will be giving us metal and oxygen. So this you will be seeing in the case of the carbonates also. You will be seeing it in the case of the nitrates also. You will be seeing in the case of the hydroxides also. Everywhere, same type of reactions that you will be seeing. For the class 3 metals, the oxide that will be formed is going to break down into metal and oxygen, because class 3 metal oxides, they are not stable to heat. And that is what we learned at the start of the lecture also, that as we move down the activity series, the affinity of the metals for the oxygen decreases. So class 1 metals, they are attracted to their oxygen, they do not decompose. Class 2 metals also, they are attracted to their oxygens, they do not decompose. But as we are moving down, we reach up to silver and mercury. The affinity of silver and mercury for oxygen decreases, and therefore it is very comfortable to leave its oxygen and form the corresponding metal. All right. So I hope you are going to remember this. You will not be able to forget this. And when you are going to look back at your lectures on the carbonates, etc. also, you are going to now remember that if an oxide is going to be formed for mercury and silver, that is going to break down further into metal and oxygen, because these metal oxides, they are unstable on heating. Perfect. Great. How do we know that as we move down the activity series, the affinity of the metals for oxygen decreases? Well, we come to know this from the Lingham diagram. So this is not going to be for the class 11 students. The class 11 students, they can either watch the rest of the portion of this lecture when they are in class 12, or just watch the lecture now so that you know exactly that you have been studied all these topics. You have to revisit this lecture for a complete understanding. So we study the Lingham diagram in class 12 when we study the metallurgical processes there, when we have to obtain a metal from its ore. All the processes happening, there is one process where you have to reduce the metallic oxide to metal. And for that, we have the understanding of this Lingham diagram, which I'm going to just now show you. So this is the Lingham diagram. So this is going to be understood only by the students who have already studied it. So for them, I am just explaining it. For the rest, please do study the chapter on metallurgical processes, and then you can understand what I'm talking about. So here what we have is on the x-axis increasing temperature and the y-axis delta G. And this delta G values is for the formation of the metallic oxides from the corresponding metal and oxygen. All right. So as we see going up the y-axis, the delta G values, they are increasing. They're becoming from negative to positive. And we all know that the delta G values, if they are negative, then the process is spontaneous. If they are positive, the process is not spontaneous. And this means that as we are going to move along the y-axis, what all formations we are seeing, the tendency of the metal to combine with oxygen to form the metallic oxide, this is decreasing. And the reverse process is becoming more spontaneous, right? So here what you can see on the top of this chart is silver and mercury. So what this means is that the tendency of silver and mercury to combine with oxygen to form metallic oxide is the least, or the breaking down of silver oxide and mercury oxide to obtain the corresponding metal is going to be the maximum. And that is what we are learning over here also, right? So as we are moving down the activity series, the affinity of the metal for oxygen is decreasing. So the affinity of mercury and silver for oxygen is decreasing to form the corresponding oxide. That is why we see that these oxides, they are unstable. When we are going to heat them, we are going to get the corresponding metal. All right, so this is what you have to remember, how we are getting these thermal decomposition of oxides, what are the results, how do we get all these. This is what we have as the understanding. Okay, next we move on to some special cases, and the first special case of thermal decomposition is zinc oxide. So zinc oxide, what you have learned is this is a class 2 metal, right? And zinc oxide therefore is not going to thermally decompose. It is not going to break down into zinc and oxygen, but something special is happening over here. And what that something special is, that zinc oxide, when it is not being heated at a normal temperature, you just see the salt, it is going to be a white colored salt. But the moment when we are going to heat it, what will happen is that this zinc oxide gets converted again into the zinc oxide only, but of a yellow color. So the color is changing on heating, and when we allow this heated zinc oxide to cool down, it becomes again white in color. All right, so what do you have to remember? Originally it is a white colored powder. When it is heated up, it turns yellow, but it does not decompose. So does not decompose it, what you have already learned, and this is now what you are learning. This is important for the qualitative analysis of the metal salts. Okay, so where do we pick this up from? We take it up from the qualitative analysis. What I'm trying to give you over here is a complete information that is required for your JEE and Neet examination. Okay, and in fact this is going to be something which is also going to be important for the solid state chapter, again class 12. So you're going to again find it over there also, a reference of zinc oxide. Now, what do you have to know more about it? Let me explain you. So what happens is that I already told you that when we are going to remove it from heat, the color is going to gradually go back to the white color. So what this means is, on a normal temperature, zinc oxide is a white colored salt. When we will heat it, it will become yellow in color. And when it is going to cool down, again, it will become white in color. And if it is treated strongly enough to very high temperature, then it is going to just simply sublime without apparent decomposition. The reason for this yellow color is that a minute amount of oxygen evaporates from the lattice. The small number of zinc atoms, they produce lattice defects which give rise to the color. I'll just now explain you this with the help of a diagram also, so that you have a complete understanding. The class 12 students, you must have studied it in the chapter solid state. If you do not remember, just revise it with me, because again this is going to be very important. Another thing which you can remember is that if we dope zinc oxide with minute traces of zinc, this will give a range of colors: yellow, green, brown and red. Okay, so let us understand now this, how zinc oxide on heating becomes yellow in color and why on cooling it becomes again white in color. So this is going to be important. Now in case of zinc oxide, what happens is that when we will be heating it, there is going to be a little amount of oxygen that is going to be lost to the atmosphere. Okay, not the whole of it, just a little bit of it. And when this little bit of oxygen, this is going to be removed, what will happen is there is going to be now an excess of the zinc ions. So if you look over here, this was the original crystal lattice, from which we have a loss of oxygen. Oxygen goes, but the electron remains to maintain the neutrality of the crystal lattice. So what happens is this excess of zinc ions, they come into the interstitial site, and along with that, the electron also gets entrapped in the interstitial site. Now this electron, this is responsible for absorbing the remaining colors of the white light, and hence what happens is there is going to be a yellow color seen for zinc oxide. I repeat once again that when we are going to heat zinc oxide, there is going to be a loss of a little bit amount of oxygen. If that goes, what is going to be left behind is zinc ions for that much amount of oxygen, and along with that electrons. These excess of the zinc ions, they get entrapped in the interstitial site, and along with that the electrons also, they go into the interstitial site. Now these electrons, they are going to absorb the remaining of the white light, all right, and therefore this will be imparting some color, and that color is going to be yellow color. So the original color of the salt was white, but when some oxygen went off, these electrons remaining, they again get excited. They can get excited, they can absorb energy, and the energy they are absorbing is in accordance with the yellow color. All right, I hope this is clear. So you will remember one very important thing, that when we are going to heat zinc oxide, there is a change in color because of the metal excess defect. All right, why is there a metal excess defect? Because we can see that we have excess of the metal ions. This is what you study in solid state. This is given in the NCERT textbook. This is given as a question in the NCERT exemplar book. This is going to be important, and this is what you have to learn in even the thermal decomposition of oxides. Next special case for heating effects on the oxides is for lead oxides. We have three types of lead oxides. The first one is lead 4 oxide. So lead 4 oxide means it is going to be having lead in the +4 oxidation state. So the formula is going to be PbO2. So PbO2 or lead 4 oxide, this is thermally unstable and it tends to decompose to give us lead 2 oxide, that is in the +2 oxidation state lead. So this is going to be PbO. So PbO2 on heating, this gives us PbO, and along with that oxygen is liberated. Now what type of PbO is formed? This depends upon the temperature of heating. If we heat it to a higher temperature, a different type of PbO is formed, and if we heat it to a lower temperature, a different type of PbO is formed. So what we have is two types of PbO. One is going to be a yellow colored PbO and the other is going to be a red colored PbO. The yellow colored PbO is called as mesicot. The red colored PbO is called as litharge. The yellow one is formed at a lower temperature. The red one is formed at a higher temperature, and the difference between the two is their crystalline structure. All right, so this is called as orthorhombic crystalline structure, and this has a tetragonal crystalline structure. right? So we have two types of lead oxide with +2 oxidation state for lead. One called as massicot, the other being called as litharge. This is what you have to remember, and the difference between the two is their crystalline structure. Now the next we have is PbO, right? So what happens when we are going to heat PbO? So when we heat PbO to around a temperature of 450 degree to 480 degrees, it forms lead 2,4 oxide, which is called as red lead or triplumbic tetraoxide. So PbO, when we are heating it to a temperature of 450 to 480 degrees Celsius, this happens in the presence of oxygen, and PbO plus O2, this forms Pb3O4, which we call as red lead. Okay, so here we have PbO, which is litharge. This is also red in color, but we call it as litharge. Okay, and Pb3O4, this is known as red lead. Perfectly fine. I hope no confusion. Now, very interestingly, what happens is when we are going to heat it at a temperature of 480 degrees Celsius, the reverse reaction is going to take place. So here around 450 to 480 degrees Celsius, what is being formed is Pb3O4. But now when you are going to increase the temperature, this Pb3O4 again breaks up into PbO and oxygen. And in this case, the PbO that we have is litharge. Okay, so I hope this is clear to you people. Very fine, no problems related to this. We have three types of lead oxides. One is PbO2, second one is PbO, and third one is Pb3O4. All right, PbO2 as well as Pb3O4, they are going to give us the same product on heating, that is going to be PbO and half oxygen. There is no change. Either you heat PbO2 or you heat Pb3O4, the product that you are getting is PbO along with that oxygen being liberated. Okay. And another important thing that I've told you is that when we are going to heat PbO, there is going to be a change in the color, and the change in the color is because of the change in the structure of the crystal lattice. In case of the yellow colored, we have orthorhombic, and in the red color, we have tetragonal. Perfectly fine. Great. Important things that you have to remember are in relation to mercuric oxide. So mercuric oxide, do you remember what we have classified mercury under was class 3. So class 3 we had mercury and silver, and there I told you that these are the two oxides which on heating they are going to decompose to give us the metal and oxygen. Right, so mercuric oxide on heating, this is giving us mercury and oxygen, but before that this is at a very high temperature of 400 to 500 degrees Celsius. They are roughly given in different books. But what you have to remember is before this high temperature, what we see is that initially mercuric oxide, which was yellow in color, this changed its color to red. And then on strong heating, this gives us mercury and oxygen. This is just similar like we had for lead also. So lead at a PbO at a lower temperature was yellow color. PbO at a higher temperature, this was red in color, litharge and massicot. I hope you all remember now. And then now on further heating mercuric oxide to a temperature of 400 to 500 degrees Celsius, what we are getting is mercury and oxygen. So what this means is that mercuric oxide is also fairly stable. We have to heat it at a higher temperature so that we can get mercury metal, and mercury metal which will be obtained will condense on the top of the test tube. Okay, and heating this is going to therefore produce highly toxic mercury fumes and oxygen, which increase the fire hazard. So this reaction, this is performed in an efficient fume hood to avoid the inhalation of mercury metal. So this is a precaution related to that as far as the qualitative analysis is concerned. I am trying my level best to give you the content from everywhere that is going to be important for your JEE Mains, Advanced and Neet examination. Now another important thing which is not related to an oxide but it is related to mercury, and I just wanted you to remember this because now it is going to be easy for you to remember. Here we talk about mercury iodide. So this is HgI2. This is a scarlet red color odorless tasteless powder. It is sensitive to light. It is insoluble in water and it sinks in water. Okay, at elevated temperature, again I'm telling you about its heating effect. At an elevated temperature, it turns yellow but turns back red upon cooling. Okay, so here we have just the opposite to that of mercuric oxide. So mercuric oxide at a lower temperature was yellow in color, at a higher temperature it was red in color, and now we have mercuric oxide iodide to be at a lower temperature red in color, at a higher temperature it is going to be yellow in color. So this is what you can remember here along with the learning of the oxides. I thought it is going to be easy here for you people to remember. So now let us quickly look at a few questions which will help us recap this lecture and also tell you the most important points from this lecture. Question number 1. Which of the following compounds will yield a metal on heating? Calcium oxide, silver oxide, sodium oxide or zinc oxide. So I would like you to first choose an option yourself and then look at the answer. So I hope you all have found it. The correct option is going to be silver oxide. We have calcium to be a class 2 metal, silver to be a class 3 metal, sodium to be a class 1 metal, and zinc to be a class 2 metal. So class 1 and class 2 oxides, they are not going to give us a product on decomposition, no decomposition product. It is going to be only for class 3 metal oxides that we will be getting a metal on heating. And it is going to be silver and mercury oxides which will give us respectively silver and mercury on heating. So correct option is going to be B choice. The next question is, the white zinc oxide turns yellow on heating because of Frankel defect, metal excess defect, metal deficiency effect, Schottky defect. So all of these defects you should know very well as far as your solid state is concerned. But here when we are talking about zinc oxide, we have already learned it is going to be a metal excess defect. So the correct option is going to be B choice. The third question is, litharge is chemically PbO, PbO2, Pb3O4 or lead acetate, and the correct option is going to be A choice. It is going to be PbO. Alright, PbO2, we do not have a name for that to remember, and Pb3O4, I've already told you that it is red lead, and the other form of PbO that we have is mesicot, which is yellow in color. Okay, so I hope all of this is very clear to you. That would be all for this lecture. I hope you've enjoyed your learning with me, and if you have, please do click on the like link and also do subscribe to the channel and also share it with your friends. In case you have any doubts, you can put them in the comment section, or you can also mail them to us at h2ochemistry@gmail.com. We will try our level best to respond you back at the earliest. And I hope you're going to be back for the next lecture where we are going to have more tricks, more concepts and more questions. So see you again. Bye bye from H2O, the A to Z of chemistry.